In section 4.4 we're going to be looking at one of the final steps in curve sketching, and that's basically looking at concavity. Concavity tells us about how the graph bends. So for instance, it could bend upward or downward. And if it's bending downward, then we call that concave down. We also call this negative concavity. Now a graph that bends down is usually pretty obvious. For instance, this has negative concavity. But sometimes it's not as obvious. So this graph also has negative concavity. This graph has negative concavity as well. Now note, for this graph in the middle, my slopes of my tangent lines are negative. These are negative sloping tangent lines. So my first derivative would be less than 0 or negative. Here, the slopes of my tangent lines are positive, so my first derivative would be greater than 0 or positive values. So you can't look at whether the first derivative is positive or negative to determine concavity. So again, for this first one, f prime of x is less than 0. F prime of x, my slope of my tangent line, is greater than 0. Now for this particular graph over here on the far left, I have positive sloping tangent lines and I have negative sloping tangent lines, so I can't distinguish between the two in this particular case. Now a graph can bend down or it can bend up. If the graph bends up, we say we have a graph that is concave up. Another name for concave up is positive concavity. So let's go ahead and look at some graphs that have positive concavity. Of course, a good old parabola is the obvious choice, positive concavity. This graph also has positive concavity, as does this graph. Now again, as before, the slopes of the tangent lines don't necessarily help us determine what's going on here. Both of these have slopes of tangent lines that are different. So if we look in this case, the slopes of my tangent lines are positive. In this case, the slopes of the tangent lines are negative. So again, positive on this side, so greater than 0, less than 0 on this side, so I have positive concavity with negative sloping tangent lines. So I can't necessarily just use something like the slope charts like I did before. I can't find just critical numbers and test those to figure out what's going on. So what we want to do is try and figure out how concavity relates to tangent lines and derivatives. In the case of positive concavity, and again the nice parabola shows this pretty clearly where I have positive concavity, my slopes of my tangent lines go negative to positive. So again, the slopes of my tangent lines are what's important here, and I also can note I also have this horizontal tangent line in between. So the slopes of tangent lines are increasing. And when we say they're increasing, we're meaning they're moving from a negative value to a positive value. And we can see again we have negative to positive sloping tangent lines. In the case where we have negative concavity, and again, nice parabola opening down always works well for that one. Negative concavity, the slopes of my tangent lines are going from positive to negative. Again, I have that 0 in between. I don't necessarily have to have that, but I do in this case. So in this case, the slopes of tangent lines are decreasing, meaning we are moving from positive to negative. So that's one of the things that gives us a hint as to what's going on when we're talking about concavity. The book defines this pretty clearly as well. Let's go ahead and look at the definition that the book gives. The book gives a definition that if we have a function that's differentiable on an open interval, this is kind of getting familiar, we use this notation quite a bit, then the function of the original graph, or the original function, is concave up on the interval if the first derivative is increasing on AB. It's concave down if the first derivative is decreasing on the interval AB. And that's exactly what we talked about up here. Concave up, I have increasing from negative to positive. Concave down, I'm decreasing from positive to negative. Now another way that we can look at this is by talking about the second derivative. If my first derivative is increasing, that tells me that my second derivative, which again is the derivative of the first derivative, is positive. If it's decreasing, if my first derivative is decreasing, that tells me that my second derivative is negative or less than 0. Let's go ahead and look at some of these changes in concavities and see if we can start trying to predict where these occur. Okay, for changes in concavities, we could have a nice graph that looks as such. Now if we look at this graph pretty clearly over here, we have negative concavity and positive concavity. This very point that change in concavity goes from negative to positive or positive to negative is called a point of inflection. And we usually represent this with a PI, point of inflection. Now again, the point of inflection is the point, and it actually can be a line as well, and we'll look at a graph like that in a moment, where a graph's concavity changes from positive to negative or negative to positive. Now how do we figure out what these points of inflection are? Well, possible points of inflection, and again PPIs are possible points of inflection, are found like critical numbers are found, but instead of the first derivative we use a second derivative. So possible points of inflection occur when the second derivative equals 0 or when the second derivative is undefined. So instead of going through and finding critical numbers for your first derivative, you take your second derivative and find those critical numbers the same way, except now we call them possible points of inflection because they are a possible point where I can change from negative to positive concavity or from positive to negative concavity. And like I said a little bit earlier, sometimes it's not a point of inflection but an entire line of inflection. Let's go ahead and look at the graph of y equal 1 over x. This is a pretty familiar graph. We use this one quite a bit, which is in the first and third quadrant. Now you can see in this quadrant 1 I have positive concavity. In quadrant 3 I have negative concavity. But we don't have a single point where my inflection changes. I have a vertical asymptote here. So where this vertical asymptote is called my line of inflection. So again, a possible point of inflection might actually be a line of inflection. It kind of depends on what the actual function is. Let's go ahead and go through an example, kind of from beginning to almost end. We almost have all the information we need for curve sketching here. Let's go ahead and look at a function and let's find critical numbers. Let's look at intervals while I'm increasing and decreasing, relative extrema, possible points of inflection, intervals where I have positive and negative concavity, and then try and look at a graph. And this will be pretty easy because we are going to use a nice little trig function, the sine function, to do this. Now whenever we're working with trig functions and curve sketching, it's pretty common to limit the interval because again, because of their periodic nature, those graphs can go on forever indefinitely, and so you'd be finding an infinite number of points of inflection, infinite number of intervals where we have positive and negative concavity. So this particular graph is limited from 0 to 2 pi. So let's go ahead and look at our first step. On our first step, we're going to take the first derivative, and the first derivative will get us information about critical numbers, increasing, decreasing intervals, and extrema. And when we're talking about extrema, we mean relative maxes and relative mins. So to start, we need our first derivative. Well, our original function is the sine of x. The first derivative of sine of x is the cosine of x times the derivative of x, which is 1. Now critical numbers occur in two places, where the function is equal to 0, where the derivative of the function is equal to 0, or where the derivative of the function is undefined. We don't have a denominator here, so I don't have to worry about being undefined. So cosine of x equals 0. Well, where does the cosine of x equal 0? At x equal pi over 2 and 3 pi over 2. So these are my critical numbers. Now, if we could keep going round and round the unit circle, I could also go to 5 pi over 2 and 7 pi over 2, and I could also move in the negative direction to negative pi over 2 and negative 3 pi over 2, but again, I've restricted my domain between 0 and 2 pi, so those are the only ones that I need to find. So to start with, I have my critical numbers. Now in order to find intervals where my function is increasing and decreasing, I produce a slope chart. Now remember, the slope chart is just a number line. And I put my critical numbers on here, x equal pi over 2 and 3 pi over 2. Now this particular number line doesn't go from negative to positive infinity like a lot of them will, because I have a restricted domain here. It goes from 0 to 2 pi. So for my first interval here, I just need to check some number between 0 and pi over 2 in my first derivative. Well, an easy one to check between 0 and pi over 2 might be something like pi over 4. Between pi over 2 and 3 pi over 2, an easy one to check would be something like pi. And between 3 pi over 2 and 2 pi, I could kind of keep with that pi over 4 multiple theme and check 7 pi over 4. Now remember, I'm just plugging these into my first derivative, which is cosine. So another way to look at this is to say, well, 0 to pi over 2 is my first quadrant. Cosine on your first quadrant is positive. Or you could plug pi over 4 in and say the cosine of pi over 4 is positive square root of 2 over 2. And remember, we don't care about the magnitude, we just care about the direction, whether it's positive or negative here. The cosine of pi is negative 1. The cosine of 7 pi over 4, this is again in the fourth quadrant, 3 pi over 2 to 2 pi. Every cosine value in the fourth quadrant is positive. So what I have here is positive, negative, positive. So I have a relative max and I have a relative min. And I also have intervals where I'm increasing and decreasing. So to summarize, my relative max is at pi over 2 and my relative min is at 3 pi over 2. Now to find the corresponding y values, I take pi over 2 and plug it into my original function. So I take pi over 2 and plug it into the sine of x to find my y value. Well, the sine of pi over 2 is 1. Now to find my relative min, I take 3 pi over 2 and plug it into my original function. The sine of 3 pi over 2 is negative 1. So those are my relative extrema. Now intervals on where my function is increasing, so I have increasing intervals. In this case it's plural intervals. Go from 0, because remember I have a restricted domain here, and 0 is bracketed in my original, so I can bracket it here, to pi over 2. Now exactly at pi over 2 my function is neither increasing nor decreasing. I actually have a horizontal tangent line there. And then I increase again from 3 pi over 2 to 2 pi, which 2 pi is bracketed because it was in the original. I also have a decreasing interval, in this case pi over 2 to 3 pi over 2. Now I'd like to point out a few differences with what we have written here. First of all, pi over 2, 1 and 3 pi over 2, negative 1 are ordered pairs. This is an x and a y value. These intervals that I have noted here are ranges or values that my x values go from 0 to pi over 2. So this is x values, and this is a list of x values. So again, be careful that you understand the difference between those. One set is an ordered pair, the other one is a range of possible values for x. Okay, so we found out everything that we could from the first derivative, so let's go ahead and go to our second step where we're looking for our second derivative. Now let's recall my original function was the sine of x. My first derivative was the cosine of x. So now I'm looking at my second derivative. The derivative of the cosine of x is negative sine of x. Now I set this equal to 0, and this will give me possible points of inflection. So possible points of inflection can occur when the second derivative is equal to 0 or when the second derivative is undefined. Either one of those cases. I don't have a denominator here, so I don't really need to worry about that. So possible points of inflection in this particular case then would be x equals, divide both sides through or multiply both sides through by negative 1. Where does the sine of x equal 0? Well, x equals 0 at 0 radians. X equals, or sine of x equals 0 at pi radians, and x equal 2 pi radians the sign of 2 pi is 0 as well. Now keep in mind that 0 and 2 pi are endpoints. And because they're endpoints, I know that they cannot be relative max or relative min, but I still should kind of think about them in my concavity chart because they're endpoints. So let's go ahead and look at a concavity chart, and in this concavity chart we'll plot our possible points of inflection. Now with a concavity chart, I want to know what's going on at 0, pi, and 2 pi. Well, 0 and 2 pi are endpoints, so I really only need to look at pi here. Now in order to figure out what's going on in my concavity chart, I need to check values in the interval in my second derivative. Okay, so 0 to pi, pi over 2 would seem like an obvious choice. Pi to 2 pi, checking 3 pi over 2 in my first derivative would be, second derivative would be an obvious choice. So I take pi over 2 and I plug it in up here into my second derivative. The sign of pi over 2 is 1, and of course this means to negate it, so I have a negative value here. Then I plug in 3 pi over 2 up into my second derivative. The sign of 3 pi over 2 is a negative 1, minus a negative is the same as a positive. So that means I have a negative concavity and then a positive concavity. Well, this is an actual point of inflection then. So I have a point of inflection at pi is my x value. Now the sign of pi is 0, so I have 0 when I plug this into my original function for the corresponding y value. I have an interval where I have positive concavity, and I have an interval where I have negative concavity as well. My positive concavity interval goes from pi to 2 pi, and I can bracket that point. My negative concavity interval goes from 0 to pi. Now notice that pi, the function is neither increasing nor decreasing, so I don't include that in either value. So we have a lot of summary information here. We have information from the first derivative, we have information from the second derivative, so we should be able to actually graph this now. And of course we could have graphed this right off the bat because we know what the sine function looks like. But we want to go through these steps of curve sketching so we can kind of understand where those values are coming from. So I go 0 to 2 pi, chop my graph into quarters here, and let's see what we have. Now looking back, I had a relative max at pi over 2, 1. So this was a relative max. And also from up above, I had a relative min at 3 pi over 2, negative 1. So this is the point negative 1. You always need to scale your graph to show these values. So I had a relative min here. Now I also had a point of inflection. Now the point of inflection occurred at pi 0. Now I got that one from right up here. So the point of inflection was at pi 0. So that means where I have increasing and decreasing functions, it said between 0 and pi over 2 my graph was increasing. And again, I'm getting these values from right up here in my first derivative information. So 0 to pi over 2, my function is increasing. It's also increasing from 3 pi over 2 to 2 pi. So it's also increasing from 3 pi over 2 to 2 pi. Now my interval that said I was decreasing, I decreased from pi over 2 to 3 pi over 2. Now I could have had decreasing this way as well, but that doesn't fit my concavity. This is positive concavity that I'm about to erase, but my graph from right up above says I have negative concavity between 0 and pi. I have positive concavity between pi and 2 pi. So this graph kind of fits everything nicely. And I could also graph the endpoints just to kind of clarify what's going on here. But again, when we look at these types of graphs, we want to look at all this information to make very clear where the function is increasing and decreasing, where I have positive and negative concavity, and also the intervals as well. Okay, let's go ahead and look at another example. This example, we're not going to be looking at a trig function. Let's go ahead and look at a rational expression this time. For this particular function, let's look at x squared over x squared minus 9. And we actually are missing one piece of information here that would make graphing this function pretty easy that we're not exposed to until the next section of section 4.5. So we're just going to have to kind of work around the fact that we don't know about horizontal asymptotes right now. But we'll try and include that the best that we can. So we want to figure out everything there is to know about this particular function, and we want to graph it. So the first step we do is we work with the first derivative. Well, the first derivative gives us information about critical numbers. It gives us information about possible extrema, relative maxes and mins, and intervals where my function is increasing and decreasing. So the first thing we need is our first derivative. Here we'll use the quotient rule, or you could flip it and use the product rule, it's up to you. So we have the bottom times the derivative of the top minus the top function times the derivative of the bottom all over the bottom squared. Now we want to look at this function in terms of, setting it equal to 0, determining where it's undefined, so we definitely need to take this derivative and simplify it. So I have my x squared minus 9. The derivative of x squared is 2x. The derivative of x squared minus 9 is 2x. The derivative of 9 is 0. It's a constant. So I'm left with x squared minus 9 quantity squared in the denominator. Well, the way this is written right now, I still don't want to set it equal to 0 to solve because it's kind of a very complicated expression. So we can see that we're going to want to simplify this. So for my first derivative, if I distribute the 2x, I have 2x cubed minus 18x. Okay, then here I have a 2x times a negative x squared would give me a negative 2x cubed. And I'm really glad we simplified this because taking my second derivative will be a lot easier now because the 2x cubes cancel. And I'm left with my first derivative as negative 18x over x squared minus 9 quantity squared. Now I want critical numbers. Critical numbers occur in two ways, where f prime of x equals 0 or where f prime of x is undefined. Well, f prime of x equals 0 when x equals 0. If we take this numerator, negative 18x, and set it equal to 0, when I solve for x, I get x equals 0. So this is a critical number. Well, this function will be undefined when x is equal to plus or minus 3. Now these values of plus or minus 3 we should talk about a little bit as well. If we look up here in our original function, right here, right away I know I have vertical asymptotes at x equal plus or minus 3 because that function is undefined. So if I can identify something like vertical asymptotes right away, that'll be really helpful. Now when I come down here, these are critical numbers. So these are all my critical numbers. But I know that plus or minus 3 will never be an extrema point. It will never be a relative max or a relative min because these are vertical asymptotes. I can't have an ordered pair that lie on a vertical asymptote. So that's kind of going to be a little bit helpful when I start to make my slope chart. So let's go ahead and look at our slope chart. Now again, the slope chart is just a number line, and then I plot my points, and I have x equal negative 3, x equals 0, and x equal positive 3. Now the slope chart, I check values in these intervals in my first derivative. And I'm looking for intervals on where my function is increasing and decreasing, and I'm also looking for possible extrema. Well, we may as well take care of this right now. Negative 3 and positive 3 are vertical asymptotes, so it's not possible for them to be an extrema point. So it's not possible for them to be a relative max or relative min. So if you can sketch it in on your slope chart, sometimes that helps clarify what's going on. So I'm going to plug in some obvious numbers here like 4, 1, negative 1, and negative 4. Now this is actually pretty easy to do. Remember, I'm plugging these in or checking these values in my first derivative. Well, let's look at the first derivative. The first derivative is right up here. If we analyze this and we recall, we're only interested in whether this first derivative is positive or negative. We do not care about the magnitude of this number. if you look at the denominator, it does not matter what you plug in here, whether it's you get something out that's positive or negative. When you square it, it becomes positive. Now the numerator is going to always be a negative times whatever it is we plug in. So a negative divided by a positive is a negative. So what ends up happening is no matter what I plug in, I just end up negating it. So if I plug in a 4, I end up with a negative in my numerator, positive in my denominator, and a negative divided by a positive is a negative. If I plug a 1 into my numerator, I have a negative divided by a positive, which is a negative. If I plug in a negative 1, I have a positive, and a negative 4, I have a positive number back out as well. And remember, you're plugging these into the first derivative. Now this is where my function is increasing and decreasing. Now, this says I have positive sloping tangent lines. Well, I have two choices for positive sloping tangent lines. Both of these have positive sloping tangent lines. They have different concavity. But if you think about it, this line does not really make sense because I'm coming up against an asymptote. I'm coming up against a vertical asymptote. So this one with positive concavity makes a little bit more sense. Okay? Now a lot of times when we can't figure out what type of concavity we have, we just make a straight line with a positive sloping tangent line to kind of represent what's happening here because we're not sure about concavity yet. But this one I'm pretty sure we're going to have positive concavity. Over here we actually have a relative max. Relative max is at the ordered pair 0, and if I want to figure out what my other value is, I plug 0 into my original function, which was way up here. Lost my fraction bar. Plug 0 into the original function, and we have, let's see what happened there. I'll just write it down again down here since it's jumping around. Our original function was x squared over x squared minus 9. So when I plug 0 into x squared over x squared minus 9, I'm left with 0. So I do have a relative max. Now let's summarize everything that we have here. I had critical numbers at -3, 0, and 3. I had a relative max at 0, 0. And that's kind of strange because you think, oh, your maximum points at the origin. You're kind of wondering what this graph might be looking at. I have vertical asymptotes I figured out at x equal plus or minus 3. And my function or my graph is increasing over the interval from negative infinity to negative 4, or sorry, negative 3s. I'm getting that point from right here. Negative infinity to negative 3, and then negative 3 to 0. Now, negative 3 is not bracketed because I don't increase across a vertical asymptote. And then I'm decreasing over the interval from 0 to 3 and from 3 to infinity. So those are kind of what I have going on so far. Now I want to figure out about concavity, because remember, up in this particular area we knew we had increasing slopes of tangent lines, but we didn't know if we had a negative or a positive concavity situation, although it's pretty easy to predict when we're given a vertical asymptote that we're up against. So the second thing we want to do is to go ahead and look at the second derivative. So let's rewrite everything. First derivative was x squared over x squared minus 9. First derivative was negative 18x over x squared minus 9 quantity squared. So we need the second derivative. The second derivative, we'd use the quotient rule, or you can flip it and use the product rule, would be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now we haven't actually taken the derivative yet, we've just kind of set everything up. So in our next step, let's go ahead and take that derivative. The derivative of negative 18x is negative 18. Minus a negative is the same as a positive here. And the derivative of x squared minus 9 quantity squared, I bring the 2 down, decrease the exponent by 1, and then I multiply it by the derivative within. Now this is going to give us a chance to show a nice way to simplify some of these expressions. if you note, I don't want to take this and set it equal to 0. It's really kind of ugly and difficult to work with. So I would like to simplify this quite a bit. So let's go ahead and look at that numerator. Now when we're working with the numerator, we're going to look for a greatest common factor. The greatest common factor is what both of these have in common. So here's a term and here's a term. What do they have in common? Well, it looks like they have an 18 in common for sure. And it looks like they have an x squared minus 9 to the first in common. So over here in this first term, if I factor away an 18, I'm left with a negative 1. We can write it as a negative 1. If I factor x squared minus 9 to the first away from x squared minus 9 to squared, I'm left with x squared minus 9. Now over here, in this second term, I factor away the 18, I'm going to be left with, it looks like 2x times 2 is 4x. And I factored away the x squared minus 9 to the first out front already, and the 18, and it looks like I'm left with this x here as well that I didn't pick up on. So we have 2x and 2x would be 4x squared. And this is all over x squared minus 9 to the fourth. Now this technique of factoring out this binomial makes things so much easier. If you go ahead and try and expand this and combine like terms and refactor it, it's going to get really ugly. So I always encourage factoring rather than expanding if it's possible. Okay, the x squared minus 9's cancel, and I'm left with x squared minus 9 to the third in the denominator. So let's go ahead and simplify this a little bit. And again, I have x squared minus 9 to the third. Now up here, what I'm left with is 18. The 18's from out front. I'm left with 9 minus x squared. And again, if I distribute the negative, I get negative x squared plus 9, or 9 minus x squared plus 4x squared. I'm going to keep simplifying this because the more we simplify it, the easier it will be to find possible points of inflection. So leave that 18 out front. 9 minus x squared plus 4x squared would be 3x squared plus 9. All over x squared minus 9 quantity cubed. We can simplify a little bit further, and again, the more you can simplify this, the better. Next I can factor out a 3. So 18 times 3 would be 54 x squared plus 3 all over x squared minus 9 quantity cubed. Now you might look at this denominator and think, okay, this factors into x plus 3x minus 3. That does not cancel up here with x squared plus 3, so we have to be pretty careful about that. So that is my second derivative. And again, I always encourage you to simplify these, otherwise you're going to have some very ugly rational expressions that you're going to have to set equal to 0 and solve. This is easy to set equal to 0 and solve. So we want possible points of inflection. Possible points of inflection occur two ways, where the second derivative is equal to 0 and where the second derivative is undefined. Well, if we look at this numerator, if we set this numerator equal to 0, there's nothing I can plug in that will ever get 0 out of this. That's a real number. So I'm stuck with this one. There is no point of inflection or possible point of inflection that will come out of setting this the second derivative equal to 0. So there's no possible points of inflection for this reason. There are two possible points of inflection for the function being undefined. We already found those. This denominator will equal 0 whenever x is equal to plus or minus 3. Well, we know that these are possible points of inflection now, but we also know they're vertical asymptotes. So they're not really possible points of inflection, they're more possible lines of inflection. So let's go ahead and check these in our concavity chart and see what's going on here. Now with our concavity chart, we still test negative to positive infinity, x equal negative 3, x equal 3, it's just a number line. And let's include these vertical asymptotes. Now because I plugged in these vertical asymptotes, I already know that negative 3 and positive 3 cannot be a point of inflection. They can be a line of inflection if they're anything at all. Now to figure out what's going on, I plug in numbers on these intervals into my second derivative. Now the second derivative has some neat characteristics just like the first one did. Notice my numerator of my second derivative will always be positive. Okay, x squared is always positive. So because this is always positive, I really only need to worry about the sign of the denominator. Because when I cube something, it could come out either positive or negative. If it was squared, of course, it would always be positive. So numbers I can check here are like 4, 0, and negative 4. So if you plug, I'll plug in the easy one here. If you plug 0 into the denominator, remember we can just ignore the numerator because it's always positive. I get 0 minus 9, which is negative 9, and negative cubed is always a negative. Okay, if we plug 4 in down here, I get 4 squared, which is 16 minus 9, which is a positive number. A positive cubed is a positive. Same thing's going to happen when I plug in a negative because I square the negative and I'll get something positive. So, looking at this, it looks like our concavity will run positive, negative, positive. So this is a line of inflection. So I can't list an ordered pair. I can't say that there's a point of inflection at negative 3, 4 or something. This is an entire line of inflection. And it's a vertical asymptote. Now, positive, negative, positive. Now if we come up and look at our slope chart, it kind of matches. I knew that I had one of these types, so it looks like I have a positive. This is definitely a negative concavity. And then I have positive back over here for my concavity. Well, when I have concavity with a negative sloping tangent line, I could have a concavity as such, or as we have over here. So here I have positive concavity, here I have negative concavity, and it's pretty clear that this positive concavity will run very nicely up against that vertical asymptote, so this makes sense. So let's go ahead and summarize what we have here and then look at a curve sketch. So we have points or lines of inflection. And again, they're not an ordered pair because these are actually lines. We have x equal negative 3 and x equal positive 3. And I guess we better back up again. We had possible points of inflection at x equal negative 3 and positive 3. We have intervals where we have positive concavity. I have positive concavity. If we look up here a little bit, I have positive concavity from negative infinity to negative 3 and from 3 to infinity. And I have negative concavity from negative 3 to positive 3. So we have everything summarized here pretty nicely. Let's go ahead and look at a curve sketch to see what's happening here. Now, something important right off the bat is to get those vertical asymptotes in, because if you have asymptotic lines, that kind of helps show what is happening here. So here's my negative 3 vertical asymptote. Here's my positive 3 vertical asymptote. And let's see what else was going on here. If we go up top to my slope chart, we had a relative max at 0, 0. So I have this upside down parabola, or this horseshoe shape, right, that's peaking at 0, 0. So this point 0, 0 is a relative max. Well, if this is a relative max, there's only one way that this can work in here. And I already have that general shape two places. I have the general shape right here in my concavity chart, and I also am given that general shape up here in my slope chart. Now to the left of this upside down parabola that we have here, this horseshoe shape, I have positive sloping tangent lines and positive concavity. So let's go ahead and have a look down here. Positive sloping tangent lines and positive concavity. Boy, this one's not so clear. I need to have positive sloping tangent lines with positive concavity. Well, let's look at a couple things. A graph like this really doesn't seem like it would make sense because it's going up against the vertical asymptote, but what's going on down here? So what might help is to actually plot a point. So let's go ahead and plot a point, let's say at negative 4. Now let's recall what our original function was. My original function was x squared over x squared minus 9. And if I plug this in, this point of -4, I only really care about whether it's positive or negative. I only care about whether that point puts me above the x-axis or below the x-axis. So if we plug in a -4, I'll get a positive in the numerator and a positive in the denominator. So that's telling me right away I'm somewhere up here, and that gives me an idea where I have this positive sloping tangent line. You can see I have my positive sloping tangent lines, and I have positive concavity. Now this also gives me a pretty good idea what's going to go on if I plug in a 4. If I plug in a positive 4, I'm going to be up above the x-axis as well, and I'll have something that looks like this. So this matches everything. Positive sloping tangent lines, positive sloping tangent lines, negative, negative sloping tangent lines. My concavity goes positive, negative, positive, just like the graph said. So this is the graph of x squared over x squared minus 9. Now, the one thing that we didn't really get to talk about here was the horizontal asymptote. This graph right here will never cross the x-axis, so I have a horizontal asymptote. This graph, this part of this graph will never cross the x-axis either, so we have a horizontal asymptote on the y-axis, maybe, or it could be a horizontal asymptote up a little bit. We really don't know yet. Maybe it's a horizontal asymptote at a half or at 1. But we really can't tell yet, so we have to figure out what's going on, and we'll get a little bit more information on this in the next section. And as it turns out, our horizontal asymptote is actually at y equal 1. So I have a horizontal asymptote right here at y equal 1. But we'll talk about that, how we figure that out in the next section when we're looking at that. But there is a horizontal asymptote at y equal 1 for this graph. Now when you're doing curve sketching, one of these problems takes a lot of time. So one of the important things is to make sure your derivatives are correct. And remember, when you're working from first to second derivative, it's easier to factor instead of expand. And when we're trying to set a second derivative equal to 0, it's easier to factor instead of expand, because then it's easier to solve because I have a numerator that's full of factors instead of a numerator that's full of terms. And again, plotting these in Maple would be a good idea. So let's go ahead and look at this graph in Maple real quick. Okay, when we're working with the Maple with this function, instead of using the putting in the function and then right-clicking and going for the plot, I'm going to go ahead and plot this using a plot command. And the reason I'm going to use a plot command is I want to be able to look at the discontinuities here. Now remember, if I had plotted this graph regularly, what would end up happening is it would basically draw a line between positive and negative infinity for my asymptotic lines, and I don't really want that. I want to see what this graph looks like without those lines connected. So I'm going to go ahead and plot this, and I'm going to use a little bit of a command here that says discont for discontinuity equals true. And let's see what that graph looks like. Well, it almost looks worse than better. But let's go ahead and rescale some of this. I think I'll go -7 to +7, and again, there's no right or wrong way to rescale these. It's just kind of a matter of preference, what shows the graph the best. Let's go ahead and have a look. Yep, that looks pretty good. So you can see here that I have a max, it's huge. So you can see here that I have that maximum value at the origin, maximum value at the origin. I have positive sloping tangent lines, positive sloping tangent lines, and then negative sloping tangent lines. I have positive, negative, positive concavity. So this graph in Maple shows us pretty clear what's going on there. Now one thing that this does not show is this horizontal asymptote that we talked about. Remember, I said the horizontal asymptote is at 1, but we really can't see that. From this graph it could be at 0 for all we know. So again, we have to figure out how we find those horizontal asymptotes, and that will be in the next section. Let's pop back to Maple real quick, and I'd like to graph the same function, x squared divided by x squared minus 9, by right-clicking and using our plots command. So here's my graph in my plots command. And let's go ahead and just fix the vertical from negative to positive 20. And hopefully we'll get an idea about that discount equals true. And here we can see it really clearly. Right here, this vertical line right here, it's being connected from positive to negative infinity, because that's all that maple does. It's like a dot to dot. So it thinks there's a dot up here at positive infinity, there's a dot at negative infinity, so let's go ahead and connect them. And so in this case, that's what this vertical line is. It's actually an asymptotic line that should not be there. When we use discount equals true, it looks at those discontinuities and it makes them show up, so we do not play dot to dot and connect those values. So again, this graph up here is using this discount equals true command. This plot down here is just using your right-click plots on the function. As neither one of them are wrong, I guess with this one, as long as you understand that these are vertical asymptotes, that's okay, because they do show the vertical asymptotes. This does not show the horizontal asymptote. When we start working a little bit more with these, it's going to be a very good idea to plot every one of these functions and come up with a nice scale and a nice graph to show what's going on here. And using this discount equal true command will help you get better graphs. In section 4.5, we actually get to figure out how to find these horizontal asymptotes, and we kind of pull all this information together to do a lot of curve sketching. Thank you.